Okay, so now after QED and QCD's Lagrangian, now in this video I will develop Lagrangian for the Electroweak theory, and before that I'm going to write some prerequisites for the Electroweak Lagrangian. So first of all, there is a gamma 5 matrix that we're going to use a lot. This is actually this thing right here, and gamma 0 is kind of unit matrix, 4x4 unit matrix. Gamma 1, or I can combine gamma 0, 1, 2 and 3 gamma 1, 2 and 3, and write it as gamma I, and gamma I are written in terms of Pauli matrices. And then gamma 5 is like this. Okay. Where these are the Pauli matrices, and if we exploit, let's log this. If we exploit gamma 5 matrix, so if you square gamma 5 matrix, we get a unit matrix of 4x4, and gamma 5 matrix is Hermitian, so gamma 5 is equal to gamma 5 dagger, and the anti-commutator relation of gamma 5 gamma mu or gamma I is 0, except that okay, so gamma matrices in general, they will satisfy this relation. Okay, so now I'm going to introduce chiral operators, or you can call them projectors, chiral projectors. Right chiral projector is 1 plus gamma 5 divided by 2. Similarly, left chiral projector is 1 minus gamma 5 upon 2. And these projectors satisfy the following properties, or I should write it here. So if you add PL and PR, you're going to get unity, and if you square PR, you're going to get PR back. Similar case is for the left chiral projector, and And you can get all of these properties just by manipulating this relationship. And 1 plus minus gamma 5, 1 minus plus gamma 5 is equal to 0. Okay, so by introducing these chiral operators, we can decompose our wave function into its left and right part. Okay, so the point of introducing chiral projectors is that because neither QED nor QCD can distinguish between the left or right-handed particles. It's only the electroweak force which can make distinction between the left and right-handed particles. So that's why we introduced this. So now let's say if we have a function and if we operate chiral operators on this, we are going to get the left-handed part of psi of x and right part of the psi of x, or we can write it like this: psi l of x plus psi r of x. Okay. So now we are taking Dirac lagrangian and we will decompose its spinor into left and right chiral components. Okay, here we go. Psi into iota gamma mu d mu minus m into psi. Now let's write psi as psi l plus psi r. Similar case for the psi. So here we go, psi l plus psi r iota gamma mu d mu minus m psi l plus psi r. So now I will write them in expanded form. Let's see. Okay, so this is the expanded form, and now we exploit the following properties. Gamma mu PR, and also we'll use this property, and after using this exploiting scheme we get. So here we can see that the first two terms are these first two terms are decoupled, where the third term, which is the mass term, is mixing left and right components. Okay, so in order to develop electroweak Lagrangian, we will assume that for Munich mass is equal to 0. So this is the assumption that we'll take, and from now on the mass of fermions is equal to 0, even though in reality it is not coherent with the experimental results, but this is how we are going to do. And another thing is that because in QCD and QED, the gauge principle required that the gauge bosons must be massless. So yeah, so gauge bosons and fermionic mass will be 0 from now on. Okay, we will see that because the fact that the gauge bosons in case of electroweak are W and W plus minus and Z0, which are in fact one of the most massive particles in standard model. But while developing this Lagrangian, we will consider the gauge bosons and also the fermionic mass to be 0, and later after we have developed the Lagrangian, we will give mass to gauge bosons and fermions by Higgs mechanism, and for now we will carry on by keeping in mind that these two fermions and gauge bosons are massless for now. Okay, so we can now get separate equations for psi r and psi l fields. Okay, so let's start from the Dirac equation. Okay, so now before writing the Lagrangian, let's introduce three fields which we are going to use throughout this derivation. Yeah. So first field will be psi1, psi2 and psi3, the three fields that we are going to use. And first we are going to write quark doublets, Q up and Q down. Okay, one thing to mention here, that is U and D does not represent up and down quark. They simply represent the up state and down state, which in case of, let's say in case of quarks, we have three up type states, which are up, charm and top, down, strange and bottom. So these are up type states and these are down type states. And in case of leptons, so for leptons we will have like this, only the left-handed leptons, left-handed quarks. So the first field, which is psi1, is basically doublets, and doublets for quarks and doublets for leptons, and U and D represent the up and down type of states. And in case of leptons, we have neutrino, three type of neutrinos: nu e, electron neutrino, muon neutrino, and tau neutrino. And down type are electron, muon, and tau. Okay, psi2 is the second field, and in which we have up type quark, the right-handed up type quark, and this is a singlet. And in case of leptons, up type neutrino, right-handed singlet. And third field is down type quarks, right-handed down type quarks, and they are singlet. Similarly, right-handed down type leptons. Okay, so these are the three fields which we are going to use. Okay, now that we have clarified that which fields we are going to use in this in the derivation of this Lagrangian, now we can write from we can start writing the Dirac free Lagrangian. Okay, remember that mass, fermionic mass, was equal to 0, so we will not write the term for fermions. Free Dirac Lagrangian. Okay, here we go. L is equal to sigma j is equal to 1 to, it goes from 1 to 3, psi j iota gamma mu d mu. I'm tempted to write m here, but remember this, no mass, because we considered mass, fermionic mass, equal to 0. So here we go. So this is our free Dirac Lagrangian under the assumption that fermions have no mass. Okay, so we can simply write this. Yeah, we can take out I, psi j gamma mu d mu of psi j. Okay, here j runs from 1 to 3 and j is equal to 1 is for the doublets, and doublets which are purely left-handed doublets. These are the one which I'm talking about. So j is equal to 1 means psi 1 represents the doublets, and psi2 and psi2 will represent this right-handed singlets respectively. J is equal to 2 for psi2 and j is equal to 3 for psi3. Okay, now that we know, so we are going to decompose our Lagrangian like this: I psi1 psi bar 1 gamma mu d mu of psi1 plus, and we are going to write this, change, we are going to use k 2 and 3 iota psi bar k gamma mu d mu psi k. Okay, again psi1 is for doublets, and k psi2 and psi3 is for the singlets. Okay, so the singlets, k is equal to 2 and k is equal to 3, they follow the same global transformation law as we did in QED case. So the Lagrangian is invariant under the global phase transformation for psi is equal to 3 and psi is equal to 2. So for k is equal to 2 and 3, Lagrangian is invariant under global phase transformation. So psi2 will transform like to the y2 beta psi2, and same goes for psi3, e to the I y3 beta of psi 3. Here y2 and y3, they will represent hypercharge. Okay, so moving on, and one more thing is that psi2 and psi3, they will follow U1 symmetry. And now in case of psi1, which is a doublet, and psi1 is a doublet, and so it follows SU2 symmetry. Okay, now in order for Lagrangian of psi1 to be invariant under global transformation, it must satisfy, first we write the transformation law for psi1 field. It will be like that. Now if we want our Lagrangian to be invariant globally, so So psi and u of L must satisfy that u psi prime into psi 1 is equal to psi 1 into psi 1 bar into psi, and also for u dagger into u into u dagger must be equal to unity. Okay, and in order to satisfy the global transformation, size should follow this, and unitary matrices UL, they should also follow this relation. Okay, so now if we look at how u of L looks like, so it looks like it has this shape, exponent, or yeah, write it like this, dot alphas, or we can write it like this, u of L is equal to exponent I psi upon 2 yeah, I was going to write it like this, of alpha. Yeah. Okay, so if we want our psi 1 field to be invariant under global transformation, so psi 1 should follow this relation, and also our UL operator should follow this. Now if we move towards the local symmetry, or the local gauge invariance, we should write B like this, and alpha as a function of x, yeah. Okay, so in case of psi 2 and psi 3, they will transform in the same way as did as the psi of QED transformed, so there will be no different. So for in case of psi, in case of psi k, means for psi 2 and psi 3, they must have the same shape as we got in case of QED. Okay, so here we are introducing G prime and B mu. Okay, so if we compare it with QED case, in QED we had E as a coupling constant which was telling us the strength of interaction, and here we are using G prime. And in case of QED we used A mu, which was the photon auxiliary field, and here we are using B mu. So this is for electroweak case, this was for QED case. Since psi 2 and psi 3 follows the U1 symmetry, so that's why I am saying on that assumption, or under that, I don't know, yeah. So on the base of that calculations that I did in case of QED, since those fields were also following the U1 symmetry, so they transformed like this, and so psi 2 and psi 3, they're also following the U1 symmetry, so they will also transform in the same way that that they did in case of QED. So yeah, no problem for psi 2 and psi 3. Now if we move towards psi 1 field, since psi 1 is a doublet, and it follows the SU2 symmetry, and SU2 is non-abelian, so eventually we are going to get an extra term like we got in case of QED. So here we go. So yeah, in for psi 2, because it follows SU2 symmetry and it is non-abelian, so we will have an extra term here. So this is this is the covariant derivative that we are going to use in case of psi 1 field, which is a doublet. Here we can see that we have an extra term iota g w mu, which is analogous to w mu, which is analogous to g mu fields in case of QCD. And in case of QCD we had G, and here we have G of in QCD we had G of S. And by definition the covariant derivative transforms as the field transforms. So the covariant derivative transforms itself as the field transforms. And here we are not going to really check that thing, that if d mu transforms in the same way as the field transforms itself, because we have done those calculations in case of QCD. So yeah, we move ahead and write d mu psi 1. So here we just have in case of psi 1, because for psi1 we have, yeah, I just written here, yeah, we have u of l and two pieces for psi1, so it will be written like this: y1 beta of x, and for u of l e to the iota divided by 2 dot alpha of x d mu psi1 of x, and for psi k it transforms like e to the iota yk beta of x d mu psi of k of x. Now here we have introduced two new fields, b mu of x and w mu of x, and these two fields transform like this: b mu prime is equal to b mu of x minus 1 upon g prime d mu of beta of x, and w mu of x transforms as sigma upon 2 dot w mu of x, or sigma I w I mu of x, where I runs from 1 to 3. So in case of QCD we had 8 fields, because we had 3 colors in case of QCD. Here we have a doublet, so the number of generators will be n square minus 1. So we have two components, the uptype particles and the downtype particles in a doublet, so 2. So we have 3 generators in case of SU2 symmetry. So we have 3 generators and one generator, one field from psi2 and psi3 field, and 3 fields from psi1. So basically we have a b mu, and we have 3 w mu i's. I runs from 1, 2 and 3. Okay, so now let's see the infinitesimal transformation. For an infinitesimal transformation we can write u of l just like we did in case of QCD. We'll have something like that, and if we see the infinitesimal transformation, infinitesimal variation in w mu's of I, we will get w mu I so this is the for infinitesimal change, and we get Levi-Civita tensor. Okay, this is a structure constant epsilon ijk, and it is similar to what we did in case of QCD. So these are the structure constants for SU2 symmetry. Okay. In case of QCD, the psi gauge fields that we found were massless, but here we know from the fact that experimentally we found that the bosons that are the W plus minus and WZ bosons have mass, and massive bosons will eventually break the symmetry. So we need our bosons to be massless. And we deal with that issue later on. For now, we are going to write our Lagrangian and see. Let's see. And here we are going to replace d mu with what we have found earlier. So this is the d mu for the psi1 field, and this is the d mu for psi k field. And remember that there are three fields. Psi k includes psi2 and psi3, which are singlets, right-handed, and psi1 is a doublet. And one more thing to remember, psi2 and psi3 follows U1 symmetry, and psi1 follows SU2 symmetry. Okay, so we are going to put in our d mu's here in this Lagrangian. Okay, so for psi k we had d mu of the same kind as we had in case of QED, with b mu auxiliary field, and for psi1 field we have a covariant derivative of the form same as we found in case of QCD. Okay, so here we go. Now I'm going to write them in expanded form, and let's see. So if I expand this, so what I will get, d mu psi2 with this term for k is equal to 2 plus psi3 gamma mu d mu psi3 for k is equal to 3. And then I'm going to have gamma mu d mu psi1, and then okay, Next I'm going to have, okay, so I'm getting I will get, okay, so gamma mu d mu psi 1. Okay, so two terms with d mu, okay, not the right choice. Okay, two terms with d mu for k is equal to 2 and k is equal to 3, and then this term from here. Now I'm going to write the other terms. Okay, for that I will get a minus sign because I have an iota here and iota inside, iota here and iotas inside, so I will get some negative terms. G prime y2 psi 2 gamma mu b mu psi 2 minus G prime y3 and psi 3 gamma mu b mu psi 3 minus G prime y1, okay, this is G, it's looking like a Z, okay, y1 psi 1 prime gamma mu b mu psi 1 minus G psi 1 bar gamma mu w mu psi 1. Okay, so if I look at these terms, I can write, I can write these first three terms by compressing them. I can compress them like this. J is equal to 1 to 3 iota J gamma mu d mu size of J. And for the let's use a different, let's choose this one. Okay, for the G prime terms, this term, this term and this term, I can also compress them. Let's see, minus G prime will come out, and let's use a different index. Let's say L, y of L, psi of L, where L goes from 1, 2 and 3, gammas of mu, b mu psi of L. And then I have a unique term at the end. Let's also highlight that so it does not feel like it's left over. Okay, so here we go, G of psi 1 bar gamma mu w mu and psi 1. Okay, so now if you look carefully, this right here is kind of free Lagrangian, Dirac free Lagrangian. Free Lagrangian looks like that, and of course without mass, because in the beginning, or in the beginning we considered fermionic mass to be 0, so this is Dirac free Lagrangian. and these right here are the interaction terms. Okay, so now we are going to work with this term, the last term, minus g psi 1 bar gamma mu w mu psi 1, and here we are going to write w mu, we write w mu in terms of Pauli matrices. So w mu is equal to w mu x, and by expanding this, psi 1 w mu 1, there are three components, sorry, not psi 1, sigma 1, sigma 2 w mu 2, sigma 3 w mu 3, and if I remind you that Pauli matrices, we also call it sigma x, that was 0 1 0, sorry 0 0 1 1, sigma 2 or sigma y was 0 minus iota 0, sigma 3 or sigma z was equal to 1 minus 1 0 and 0. So okay, now we are going to write w mu in terms of Pauli matrices. So when we are going to multiply w1 with sigma 1, we are going to get 0 w mu 1 w mu 1 0 plus 0 minus iota w mu 2 iota w mu 2 0 plus w mu 3 0, sorry, I should have given it more space. Okay, 0 minus w mu 3. Okay, now adding them all together, what I will get is 1 upon 2 times, so this time this I get a w mu 3, here I get w mu 1 minus iota w mu 2. Okay, I should have written it more closely so it looks more like a matrix. W mu 2, okay, w mu 1 iota w mu 2. Oh yeah, it should have been here. W mu 1 plus iota w mu 2, and now it here, no, okay, minus w mu 3. Okay, so now I have w mu like this, and now we are going to define auxiliary auxiliary fields w plus minus, and these will be our physical fields. So we define them like this: w plus minus w mu 1 minus plus w mu 2 divided by square root of 2 and w's hold this property. Well, okay, these fields will correspond to the physical w plus minus bosons. These fields will correspond to the physical w plus minus bosons which have been found experimentally. Okay, we are getting close and close. Now that we have defined the auxiliary field w plus minus, now let's go back to this term that we took outside. Let's copy it from here, paste it right here. So psi1 is a doublet, sorry, q down, and get here it's psi bar, so it will be a row matrix. Sorry, I'm keep writing mu u q down, gamma mu, and then w mu, which is matrix of w3 mu, and square root of 2w mu minus, as we have defined it right here, sorry, here. So here we get square root of 2w mu plus w mu 3, and then we have psi1 w q u and q down. Now we're going to multiply gamma with this matrix, and we get something like this: q up and q down. And when we multiply with gamma inside this matrix, and we multiply this matrix with psi1, we get gamma mu w mu 3 q up plus square root of 2 gamma mu w mu minus q down. Here we get square root of 2 gamma mu w mu plus q up plus gamma mu w mu 3 q down, and when we multiply it all together, we get g q up gamma mu w mu 3 q u q up and square root of 2 q bar u gamma mu w mu minus q down plus square root of 2 q bar down gamma mu w plus mu q up plus q bar down gamma mu w mu 3 q down. Okay, so for the time being we are only considering the off diagonal terms, which are the one with w minus and w plus. So why we are considering only the off diagonal terms? Because we will divide the Lagrangian into Electroweak Lagrangian, I mean this specific part, into two parts, the Lagrangian for the neutral current and Lagrangian for the charged current, and W plus and W minus will be for the charged current part. So okay, so now I'm considering the off diagonal term, so let's write off diagonal terms. So it will be minus square root of 2g q bar gamma mu w mu minus and 1 minus gamma 5 upon 2 q down, because these are left-handed, plus q d bar gamma mu w mu plus 1 minus gamma 5 upon 2 qu. Okay, so this one right here is the Hermitian conjugate. And now if I rewrite this term for the leptons and quarks all together, so I get square root of 2 divided by 2 g up type quarks gamma up type quarks type quark gamma mu w mu minus 1 minus gamma 5 down type quarks plus up type leptons gamma mu w mu plus 1 minus gamma 5 downtown leptons and their emission conjugate. Okay, so after writing this, we have now the charged current term of our Lagrangian. So it will be square root of 2 divided by 2 g into u bar gamma mu w mu minus 1 minus gamma 5 down plus, okay, so here it is, I corrected this one. Okay, w plus mu 1 minus gamma 5 plus Hermitian conjugate. So here we have the charged current term of our Lagrangian. Now if we go back a little bit, this was our Lagrangian. Sorry, let me take the highlighter. Okay, this was our Lagrangian, and just now we have solved this term right here, and we got charged current term from here. Now we are going to consider the diagonal terms here, diagonal terms, in order to get the neutral current part. So the left, I mean what we, okay, so I mean these two terms here, this one and this one will correspond to the off diagonal, so diagonal terms, and correspond to the neutral charged currents. Now I'm going to write the whole Lagrangian so far of the Electroweak. First we had the free Lagrangian. I'm going to denote that free Lagrangian here, which is right here, with L0. So I have L0, I have charged current term that I just calculated right now. Then I have the left hour, which corresponds to the neutral current, YL psi bar of L gamma mu P mu psi L minus G psi 1 bar gamma mu sigma 3 or 2 dot W mu 3 psi 1. Okay, now we look at the neutral current term for the Lagrangian, which is minus G psi bar 1 gamma mu sigma 3 over 2 3 psi 1 minus G prime, which is equal to 1 y of j. So I'm just changing the index here. Psi bar of j gamma mu b mu and psi of j. So now I mean there are three bosons for Electroweak: W plus, minus, and Z0 that we find experimentally. So we have already dealt with this W plus minus term, which corresponds to the neutral charge current. Now our natural approach would be to think W3 mu as as Z0, and we correspond B mu with A mu, which corresponds to the photon auxiliary field of QED. But it is not possible, because Q in case of QED, the Q which corresponds to the charge is not same as Y in Electroweak, because Y here is not same as Q of QED, because Y here is hypercharge. And secondly, photon, if we look at the a mu, which corresponds to the photon, which is the boson in case of QED. So photon cannot distinguish between the left or right handedness. So for up and down states, photon will see y2 and y1 as equally, which is not true, as we know that. So we cannot do this correspondence between b mu and a mu. No, we cannot do that. So what other thing, what is the solution to this problem? Because neutral current can happen via photon or Z0, but since photon cannot distinguish between the left and right-handed particles, and since Y here in Electroweak lagrangian is not same as the Q, so we cannot treat b mu as a mu. So the solution to this problem is what we call is electroweak mixing. Electroweak mixing angle, or we call it Weinberg angle. And we are going to write W mu 3 and B mu as a superposition of gamma and Z0. So how do we do that? So actually the thing that I'm going to write here right now is called the electroweak unification. So according to electroweak unification, W mu 3 is actually the superposition of Z mu and sine and A mu, and theta W here is the Weinberg angle or the mixing angle, and this is something which we can find experimentally. So we are good with that. B mu can be written as the superposition of again Z mu and A mu. So this thing right here is called electroweak unification. Electroweak unification. Cool. Okay, here Z mu and A mu represent the physical state, physical field Z0 and gamma. So Z mu and A mu correspond to the physical fields Z0 and gamma. Now we need to check that neutral current term actually contains the electromagnetic term. For that we need two statements, and both must hold. So the electroweak unification So the first statement is that g sine of theta w is equal to g prime cosine of theta w. Both must be equal to E. So this right here is the Electroweak unification. And the second statement is the Kalman-Nishijima formula. Y is equal to Q tilde minus T3. Okay, here T3 is the third component of weak isospin. Y is the hypercharge, and I have written a tilde over Q, and the reason is that Q here is a 2 by 2 matrix, and we will see later why I've written tilde over here. Okay, anyway. So third component for up type quark is half, and for down type it's minus half. So Y for the up type is Q up minus half, which is equal to, for up type we have charge 2/3, so we get 1/6. And similarly for the down type we have charge minus 1/3, and we have weak isospin minus 3, so 1 over minus 1 over 2, so it will become plus 1 over 2, so we get 1 over 6 here. So we can see that up and down state quarks have the same hypercharge, and we can also check that this formula also holds for leptons, so you can check. Anyway, now we are going to substitute W mu 3 and B mu in our Lagrangian for the neutral current. So here we go. We take this from here. We paste it here, and then we substitute our Electroweak unification into this neutral current. We get gamma mu sigma 3 over, okay, it was 2 not 3, sigma 3 over 2 W mu. For W mu we are going to put cosine of theta Z mu and sine of theta W mu. So cosine of theta W Z mu plus sine of theta W A mu psi 1 minus G prime L starts from 1, so yeah, I used the index j starts from 1 to 3, y of j, psi of j, gamma mu minus sine of theta w z mu, okay, very sloppy writing, theta w z mu plus cosine of theta w a mu and psi of j. So after simplifying things, we get minus g psi 1 of j sigma mu gamma mu sigma 3 over 2 cosine of theta w z mu plus sine of theta w psi 1 minus g1 y1 psi 1 bar gamma mu minus sine of theta w plus cosine of theta w, okay, here I forget z mu plus cosine of theta w a mu psi 1 minus, okay, so what I did, I took the psi 1 term from here and write it explicitly here, and now I'm going to write the second and third component here separately. Yk, where k runs from 2 to 3, and gamma mu minus sine of theta w z mu plus cosine of theta w a mu psi of k. Okay, now we are going to separate all the terms, separate all the terms with a mu, and that will be our neutral current part mediated by the gamma, and then we will separate terms with z mu, and that will be the neutral current term mediated by the z0. Okay, so minus g psi 1 bar gamma mu sigma 3 upon 2 and sine of theta w a mu psi 1 a mu, okay, I forget here a mu, here we have a mu, okay, a mu of psi 1 minus g prime y1 psi 1 bar gamma mu cosine of theta w a mu psi 1 minus g prime k is equal to 2 and 3 y of k psi of k bar gamma mu cosine of theta w a mu psi of k. So these are the terms which are mediated by gamma, and here we are going to use the first postulate of Electroweak unification, that is g of sine theta w sine of theta w is equal to g prime of cosine of theta w is equal to e. So now we get, after using this unification, so g, okay, g sine of theta w, g prime cosine of theta w, g prime cosine of theta w, for all these three terms we are simply going to write e. So minus e psi 1 power gamma mu sigma 3 over 2 a mu psi 1 minus e y1 psi 1 gamma mu a mu psi 1 minus e k equals to 2 and 3 y k psi k bar gamma mu a mu psi k. So this is the neutral current term. We can simplify it more by, let's see how. Okay, these are the terms which are common in both first two terms. From here we get sigma 3 by 2 plus y sigma, okay, from here we get this, and from here we get this, yes, y1, and on the other side we are going to write a mu of psi 1 minus e k is equal to 2 and 3 y of k psi of k gamma mu a mu psi of k. So this is the neutral current term which is mediated by the photon. So since we are trying to achieve QED like Lagrangian, so we are going to compare sigma 3 over 2 plus y1 with q tilde, and q tilde is, as I told you earlier, is a 2 by 2 matrix in SU2 group. Okay, so psi 1 is a doublet for both quarks and leptons. And as I have shown you earlier that hypercharge for we can check the hypercharge for the up-type quarks and the down-type quarks. For up-type quarks, let's say for the up-type quarks, q up is equal to 1 over 6, and the same is for the down-type quarks. Similarly, for up-type leptons and for down type leptons, we get 1 over 2, and for singlets, these are basically left-handed, and for singlets I get for up type 1 over 6, 5 for the, and this for the 2, down type I get 1 by 6, so this is same for both. And for right-handed 3 I get 1 over 2, and same for the lepton, that is 1 over 2. So now if I compare this, I can clearly see that Q1 is equal to sigma 3 over 2 plus Y1, and Q2 is equal to Y2, and Q3 is equal to Y3. This allows me to write the neutral current part of Lagrangian in a more compact way by simply writing, now I'm going to change the index again. I am simply writing Qj, where J runs from 1 to 3, and these are the 3 values of Q. And next I'm going to write psi bar J, gamma mu, A mu, psi J. Yeah, it can look more pretty. If I take out A mu, J is equal to 1 to 3, Q psi bar gamma mu Qj psi J. So yeah, now it looks more pretty, more compact, more pretty. So this describes the interaction between photon and the fermionic current. Q is again here not fixed by the theory, just like it was not fixed in the case of QCD. Now I'm going to write the terms corresponding to Z mu. So the terms corresponding to Z mu minus G psi 1 bar gamma mu sigma 3 over 2 cosine of theta w Z mu psi 1 plus G prime Y1 psi 1 gamma mu sine of theta w Z mu psi 1 plus G prime k is equal to 2 and 3, y of k psi bar of k gamma mu sine of theta w Z mu yk. Okay, again here we are going to use the Electroweak unification that we have used earlier. it is right here. So we will use this unification and rewrite it. So I'm going to write it by summarizing sine of theta w cosine of theta w. So I'm simplifying things a little bit. So cosine of theta w psi 1 bar gamma mu sigma 3 over 2 z mu psi 1 minus sine square of theta w psi 1 bar gamma mu z mu psi 1 minus sine square of theta w 2 and 3 y of k psi bar of k gamma mu z mu psi of k. And I'm going to use this identity, trigonometric identity here, theta. So by rewriting this using this trigonometric identity, I'm going to get theta w cosine of theta w, and to take z mu common, or my professor used to say that taking z mu in evidence. Well, sigma 3 over 2 psi 1 minus sine square of theta w psi 1 bar gamma mu sigma 3 over 2 plus y1 psi 1 minus sine square of theta w k is equal to 2 and 3 y of k psi bar of k gamma mu psi of k. And here again this will be q1, and here in yk we will get q2 and q3. So I'm going to write it down. So the neutral current mediated by the Z boson is finally here. Finally we are getting somewhere. Okay. Psi 1 bar gamma mu sigma 3 over 2 psi 1 minus sine square of theta w j equals 1, runs from 1 to 3, and I'm going to add this term with this term since both terms has sine square of theta w in common, and I'm going to write sigma 3 over 2 plus y1 as q1 and y2 and y3 as q2 and q3. So yeah, works. If it works, why not do it? We already have suffered a lot. Okay, here we go. So now that we are here so far, I'm going to introduce two new quantities. They are called axial vector and vector couplings. So I'm going to call them AF, axial vector. Okay, first try. Axial coupling, VF, vector coupling. So AF will be equal to the third component of weak isospin, which is this, and VF will be axial coupling into 1 minus 4 times absolute value of Q into sine square of theta W. Okay, so we can check the values for the down type of quarks, and we can check the values for AF, values for the AF and VF for the down type quarks. And for quarks, the calculations are simple. You can do it for yourself. I'm just going to write down the result here. For down type quarks, it will be minus 1 over 2, and VF is going to be 1 over 2 minus 1 plus 4 over 3 sine square of theta W. So for up-type quarks, okay, I think I got it wrong here. So for up-type quark, it is 1 minus 8 upon 3, and for up-type quarks, AF is equal to 1 upon 2, and for down-type quarks, AF is going to be minus 1 over 2, and VF is going to be 1 over 2 minus 1 plus 4 over 3 into sine square of theta W. And for leptons, it will be for up-type leptons, AF will be 1 over 2 and VF will be 1 over 2. And why it is 1 over 2? Because the fact that for up-type leptons, the charge is 0, because neutrinos do not have any charge. That's why we have this only half. And for down-type, up-type, which are neutrinos, and down-type, AF will be minus 1 over 2 and VF will be half into 1 minus 4 times sine square of theta W. So now we can rewrite Z, the neutral current mediated by Z boson, in terms of axial and vector couplings. So I'm not going to do the simplification here. I'm just going to write down the result. So Z mu is equal to minus E over sine of theta W cosine of theta W Z mu. Okay, I'm here writing size in terms of F, and for fermions, since quarks and leptons both are fermions, so I'm going to use the notation F here. So F1 gamma mu AF into 1 minus gamma 5 into F1, or I can write T2 outside here, yeah, minus 2 sine square of theta w, j runs from 1 to 3, qj gamma mu qj, okay, so it will be psi j, yeah, fj, sorry, I decided to write f instead of psi, so yeah, fj. So after simplifying this, we are going to get 2 sine of theta w cosine of theta w z mu j f j gamma mu vf minus af into gamma 5 fj. Beautiful. Okay, so this is, finally I can highlight it, yeah, so this is the neutral current term mediated by the Z boson. So now, so far, the Lagrangian for Electroweak, how it looks like now. So Electroweak Lagrangian, first we had the Dirac free Lagrangian, yeah, it feels good to write because we spent too much time on this. Then we got a charged current term mediated by the W plus and W minus. Then we got neutral current term mediated by gamma photon, and then just right now the neutral current mediated by the Z boson. Okay. So this is the Lagrangian that we have got so far. So what kind of interactions this Lagrangian can define? So it can tell us the interaction of fermions mediated via photon, interaction of fermions via Z boson, and yeah, by W minus, yeah, and then okay, one thing to note here is that it can be either plus or minus, I don't know, yeah, so only W plus and minus, only these bosons can change the flavor of the fermion. So Z and gamma, they are flavor conserving, neutral currents, they will define the neutral currents and they will be flavor changing mediated by the gamma or Z. But on the other hand, W minus and W plus, these bosons will change the flavor too, so they are not flavor conserving. Okay, so just last thing, actually not the last thing. Why not the last thing? Because Electroweak Lagrangian is, you know, it's like a bone in the neck. This is the idiom that we used to say in Pakistan. So first of all, we have our free Lagrangian. So I'm just going to write the terms corresponding to L0, LCC, LNC through gamma, LNC through Z boson in full form, just to get a feel of satisfaction. G U uptype W mu minus 1 minus gamma 5, downtype L gamma mu W mu plus 1 minus gamma 5 to L plus the Hermitian conjugate minus E A mu. So this is the term corresponding to the neutral current mediated by the photon, and lastly the term, okay, I'm going to write minus here. So this is the last term which corresponds to the neutral current mediated by Z boson. J, and yeah, it was also convenient to use this to make distinction. Anyway, so this is the last term which corresponds to the neutral current mediated by the Z boson. Okay, now I can highlight it with a good, no, let's use some different color. Okay, so yeah, here we go. This highlighted mess right here is the Electroweak Lagrangian so far. Why I'm saying so far? Because right now we still have to write the kinetic energy term for this Lagrangian and this kinetic energy term, believe me or not, yeah, believe me, and believe me that this is a mess. That's why I'm going to deal with this term in the next video. Yeah, if I find some courage, I will do it. Anyway, now let's analyze the terms that I have written so far, what they are representing. So first of all, the interaction between the first term is showing or interpreting, yeah, the interaction between a fermion and a photon, which is basically a neutral current, and I'm talking about this one right here, and this vertex right here is simply minus e q of j. The second one is again neutral current mediated by the Z boson. Here the fermions can be charged or they can be neutral, and the vortex here is proportional to, let's write it with a different color, yeah, is proportional to, let's make some way, to this term right here. Okay, also let's highlight this, yeah, and yeah, also also this. The third and the fourth diagram right here, Feynman diagram, describe the charged current mediated by the W plus minus bosons, and the vortex here is proportional to this. Let's highlight it with a different color, yeah, is proportional to this thing right here, this thing, and with this. So yeah, I wanted to use a different color. Okay, this and this is proportional. This vertex right here, this one and this one is proportional to this and this, and yeah. Okay, so W couples two particles of the same doublet whether they are quarks or leptons. What does that mean? It cannot couple, let's say the up type of quark with the down type of lepton. So it will couple two particles of the same doublet. Anyway, let's put an end to this video, and in the next video we will deal with this mess right here. Ciao out.